Expressions for fields and potentials can be written as series expansions called multiple expansions. The first term in the multiple expansion is the monopole term, the second term is the dipole term, and the third term is the quadrupole term. The leading non-zero term in the multiple expansion is the dominant contribution to the field or potential. Here are some examples of multiple expansions. Some of these terms may be zero for certain distributions of mass, electric charge, and electric current. We are already familiar with the monopole terms, as they have the same form as the corresponding equations for point particles. Note that the net mass or electric charge in these expressions would be for the entire distribution of mass or electric charge. The different terms in the multiple expansion of the electric potential and field have different dependencies on the distance from the center of the distribution of electric charge. This results in the higher order terms in the multiple expansion, contributing proportionally less and less to the potential or field as the distance from the distribution of electric charge increases. The electric potential of this system of two charged point particles at the position P can be determined using the equation for the electric potential of a point particle. We can then expand this expression in a series of terms with different dependencies upon the distance r. The first term is the monopole term and is equal to 0 since the net electric charge of the system is 0. The leading non-zero term is the dipole term, and this dipole term dominates when the distance r to the position P is much, much larger than the distance d between the two charges. For this reason, the system is commonly referred to as an electric dipole. Each term in the multiple expansion is frequently expressed in terms of the corresponding moment, monopole moment, dipole moment, etc. These moments are vector quantities and provide a description of the associated distribution of mass, electric charge, or electric current. Here is the equation for the dipole term in the multiple expansion of the electric potential. The electric dipole moment is denoted as mu sub e. The unit vector r hat points from the dipole to the position where the electric potential is measured, and the variable r is the distance from the dipole to that position. The electric dipole moment is a vector that points from the negative charge in the dipole to the positive charge in the dipole. We can also express the equation for the dipole term using the angle theta shown in the figure. We can determine the magnitude of mu sub e from our previously derived multiple expansion for the electric potential of this system. Comparison of the two expressions for the dipole term show that mu sub e is equal to the product of q and d. The variable q in this expression is the average of the absolute values of the electric charges in the distribution. The variable d is the distance between the charges. Consider this rigid rod, which contains both positive and negative charges. We can determine the electric potential of this rod at the position P using the equation for the electric potential of a uniformly charged rod. Indeed, this system is simply the sum of a positively charged rod and a negatively charged rod. We can then expand the expression for the electric potential as a series. For simplicity, let's assume that r is much, much greater than L, so we can truncate the series after only two terms. As expected, the electric monopole term is 0, since the net electric charge of the system is 0. The leading non-zero term is the electric dipole term. We can determine the value for the electric dipole moment by comparing this result to our general expression for the electric dipole term. From this comparison, we see that the magnitude of the electric dipole for this system is q times L divided by 2. We can perform similar calculations with the magnetic potential and field. The The different terms in the multiple expansion for the magnetic potential and field have different dependencies on the distance from the center of the distribution of electric current. This results in the higher order terms in the multiple expansion contributing proportionally less and less to the potential and field as the distance from the distribution of electric current increases. For example, the equation for the magnetic field of a ring of current can be written in a form that can be expanded in a series more easily. This allows us to write the multiple expansion of the magnetic field of this system. The monomole term is 0 as expected, since magnetic monopoles cannot exist. The leading term in the expansion is the dipole term. For this reason, we commonly say that a magnetic dipole is the fundamental type or source of magnetism. The direction of the electric field along the axis of the electric dipole moment is the same as the direction of the electric dipole moment. Similarly, the direction of the magnetic field along the axis of the magnetic dipole moment is the same as the direction of the magnetic dipole moment. The vector mu sub m is referred to as the magnetic dipole moment. We can determine the magnitude of the magnetic dipole moment from the multiple expansion of the magnetic field of the system. For the ring of current, this comparison shows that the magnitude of the magnetic dipole moment is equal to pi I r squared. Thus, the magnitude of the magnetic dipole moment of the ring of current is equal to the product of the current in the loop and the cross-sectional area of the loop. Finally, we can also use multiple expansions for the gravitational potential and field. The different terms in the multiple expansion for these quantities have different dependencies on the distance from the center of the distribution of mass. This results in the higher order terms in the multiple expansion contributing proportionally less and less to the potential and field as the distance from the distribution of mass increases. For example, the gravitational potential of this system of identical point particles at the position P can be determined from the equation for the gravitational potential of a point particle. Expanding this expression in a series gives us the following equation. The leading term in this expansion is the gravitational monopole term. This term dominates when r is much, much greater than d. Notice that there is no gravitational dipole term. This is always true, since there is only one type of mass.